Hi, welcome to Unit 5 AP Physics C, Electricity and Magnetism. Here in this video, we're going to talk about magnetic flux. Okay, so we've talked about electric flux. So it's going to be a very similar concept. The idea of that magnetic flux is just simply the amount of a magnetic field that goes through a particular surface. So it's going to be measured in Webers, and Webers is named after Wilhelm Eduard Weber, who was a German physicist who worked with Carl Friedrich Gauss on many concepts. And so the equation for magnetic flux, you'll see, is very similar to electric flux. So it's phi sub b is going to be equal to the integral of b dot dA, right? So you can see that it is going to be a dot product, and it's going to be, so the magnitude of that will be BA cosine theta, right? And so something to note is that the magnetic field is going to be the amount of magnetic flux per unit area, and sometimes we'll call this flux density. So simply know if B is equal to magnetic flux over area. But again, if you do a little bit of algebra here, you end up with that magnetic flux equals to BA. Okay. And so you can see in the diagram here, there's ways that we change the amount of a magnetic field that passes through that particular area. And there's going to be three ways to do it, right? One, we change the strength of B. So we make that magnetic field stronger or weaker. The second thing that we do, is we change the size of A. Right? We make it a bigger area, we make it a smaller area, right? Because again, it's going to be predicated on how much is fitting through that area per unit, or at that particular time. And then the last thing that you could see here, like max flux, zero flux, and then any flux, right? You can see that we can change the angle at which that surface is inside that magnetic field. Right? The closer I am to 90, the greater the flux, right? The closer I am to 0, which means it's a parallel, okay? Excuse me, it's perpendicular, okay? So the closer to 0 degrees between them, between the surface and the magnetic field, that's what we want. We want 90 or 0 degrees. And then when we're perpendicular, we have 0 flux. I apologize for that. And so the amount of magnetic field through a closed surface is given by what is called Gauss's law of magnetism. So we say phi b is equal to the integral on a closed surface of BA, excuse me, it should be B dot dA. So B dot dA, which is going to be equal to 0. Again, this is on a closed surface. Okay, so things that you could do here, I mean, the simple application of the law is the very simple way, right? You'd be given surfaces and magnetic fields that pass through it, and then you have to calculate, what is the flux, or you may, kind of in the opposite direction, you may be asked, given the flux, given the area, find the strength of the magnetic field, and so forth. So let's look at, it's actually a couple of examples that's going to be stuck on one slide. So let's look at these two examples. So you have a uniform magnetic field of 0.80 Tesla acts in the positive y direction as shown. Okay. And so if you notice, the y direction is actually pointing to the right. So we have this magnetic field passing through this surface. Okay. So that's our B, 0.80 Tesla. Calculate the flux through surface ABDE, and then the flux through the surface ABCF. Okay, so something we need to do is figure out the dA. Now, ABdA is actually the backside of our shape here. So something that you see, the angle between the field and our surface is 180 degrees. So I start with my equation. So magnetic flux is BA cosine theta. And so I got 0.80, right? And now my surface area, I got a side of 4. And so I've got side of 4 and then another side of 3.5. So it's 4 times 3.5 cosine of 180 degrees, right? And I find that the flux through that surface is going to be equal to negative 11.2 Webers. Okay, again, negative because between the surface and the magnetic field is 180 degrees. All right, so let's do the second surface, ABCF, which happens to be this kind of tilted surface. Now, something that we need to figure out is here's our surface, our dA. We need to find the angle between them. Okay, and if you do a little bit of remember a little bit of trig, okay, you find that that's part of a 3, 4, 5 triangle where the angles are going to be 53, 37, and 90. Okay, and you'll find that the surface is tilted at 53 degrees. So I would say phi B is equal to BA cosine theta. It's a same amount of magnetic field. Now my area is going to be 3.5 times 5, right? Because it's it's our front surface. So 3.5 times 5.0 times cosine 53. All right, plug that into our calculator, and we find that we have a magnetic flux of 8.42 Webers. All right, now here's the next one. So now we have a uniform 2.0 Tesla magnetic field passing through a circular loop with a radius of 0.2 meters that has 4 turns. Now we're going to calculate the flux through the loop. All right, so here's my 4-turn loop, right? I've got a magnetic field passing through the loop. So now imagine the magnetic field is passing through 4 separate loops in that case. So my equation now will include this n value, which is the number of loops. Okay. We didn't do anything for that previous question because technically it was like one surface, right? One loop passing through it. Okay. And so I would do 4 times my B, my magnetic field strength, which is 2, times my area, which is pi times 0.2 squared. Okay, and you find that when you plug that in, your magnetic flux will be 1.0 Webers. Okay, so that's how we determine the magnetic flux, right? And we're going to come back to that equation when we talk about Maxwell's laws. But in the next one, the next video, we're going to talk about induced electromotive force.